My name is Jungseok. I and my co-authors Michael Fulton and Junaed Sattar are from the Interactive Robotics and Vision Lab, Minnesota Robotics Institute, University of Minnesota. I will present our paper on a generative approach towards improved robotic detection of marine litter. Research in our lab focuses on perceptual, cognitive, and interactive issues in underwater robotics, and some of our robots are seen here. One of these projects focuses on visually finding and localizing trash. This requires accurate detection of highly deformed objects. However, accurate deep object detectors require a large training dataset, and all the available underwater datasets have small exemplar imagery, often much smaller than popular terrestrial datasets such as COCO dataset. Underwater domain-specific challenges also make it infeasible to train on terrestrial datasets. Objects, particularly plastic, deform underwater quite significantly with time. Additionally, due to color absorption, appearances of objects vary with depth and images are blurred and distorted. In this paper, we propose an approach to expand an existing small dataset of underwater trash to improve their visual detection. Specifically, we developed a generative model using a two-stage VAE with a small training dataset to generate synthetic trash images. We evaluate this approach on underwater trash classification tests by training detectors on purely real, purely generated, and mixed datasets. Various generative models, including VAE, GAN, have been proposed to generate realistic imagery. To generate realistic underwater images, there are generative model-based studies, but they often fail to reproduce the distortion seen on objects after prolonged underwater exposure. Methods such as UWGAN, WaterGAN, as shown on the right, successfully generate water-distorted images. However, distortion of the shape of objects are rarely noticeable. We take the following approach, focusing on generating images of plastic bags and bottles, which are very common items found in marine litter. We first build a dataset using real images of underwater trash. We then train the VAE model on this dataset to generate synthetic images. We filter out poor quality images using a binary classifier and append the high quality images to the dataset. Finally, we evaluate the effectiveness of the generated images using a multi-class object classifier. Specifically, 3 green color models shown on the flowchart are trained models. We collected roughly 800 images of plastic bags and 300 images of plastic bottles from Junaed dataset and sources on the web such as YouTube videos. To train and test the multi-class classifier for model evaluation, we collected 2 additional classes of dataset with images of species of fish using the QUT fish dataset and empty underwater scenes with imagery from web search. With image augmentation techniques such as flipping, rotation, etc., we increased the number of images for each class to 3,000 images. The VAE aims to learn a generative model to faithfully reproduce input data. It samples noise from latent space and generates images using the noise. It consists of 2 neural networks, termed the encoder and the decoder. Throughout training, the encoder learns to generate parameters of the Gaussian distribution where noises are sampled from. The decoder learns to generate images using noise from the encoder. Compared to generative adversarial network, or GANs, the VAE models are mathematically well-grounded and provide stable training dynamics. However, the VAE models require Gaussian assumptions for the encoder and the decoder, and GANs have shown to generate sharper images than VAs. To compensate the weakness of the VA models, we take the two-stage VA model. It adds another VA stage on top of a regular VA, helping to generate close-again sharp images while providing stable training dynamics. It has been shown that the second-stage latent variable follows standard Gaussian distribution assumption at the global optimum, and this is why it can generate sharper images compared to the standard VA models. We find the minimum number of dimensions required to preserve 95% of the training set variance using PCA and utilize this to choose the dimension of the latent space. The plots on the right side show the analysis for plastic bags and bottles. As can be seen, plastic bags require higher dimensions to cover 95% variance since they have more randomness in their shapes compared to plastic bottles. Additionally, we use MA or mean absolute error with the two-stage VA model as a stopping criterion. This video highlights the result of the proposed generation process. Firstly, it shows the generated images with a single-stage VA. And then followed by plastic bag and bottle images generated with the two-stage VA with increasing training epochs. The high-quality filtered images are shown in the end. We evaluate this approach on underwater object classification tests by training detectors on purely real, purely generated, and mixed dataset. In both plastic bag and bottle classes, the classifiers trained with the generic dataset and mixed dataset outperform the ones trained with the real only dataset, as shown in the red colored boxes. F1 scores of generated and mixed datasets are higher or equal to the ones of the real datasets for both plastic bag and bottle cases. This shows that the generated images can be used to augment real datasets. VE-based generation model in the pipeline generate realistic images while being less sensitive to hyperparameter values during training compared to GAN-based models. This approach could be applied to any data-dependent test for which collecting more images is infeasible or challenging at best. We plan to train a multi-class trash detector trained with this expanded dataset to deploy onboard a physical AUV platform for field trials in open water environments. We thank our sponsors for supporting this research, and thank you for watching our presentation. Additional information is available at these URLs and web resources. Thank you.